Welcome to AI Unraveled, your daily briefing on the real-world business impact of AI. Are you preparing for the challenging Google Cloud Professional Machine Learning Engineer certification? This episode is your secret weapon. In less than 18 minutes, we deliver a rapid-fire guided study session packed with 10 exam-style practice questions and actionable study hacks to lock in the key concepts. We cut through the complexity of Google's powerful AI services, focusing on core topics like MLOps with Vertex AI, large-scale data processing with Dataflow, and feature engineering in BigQuery. This isn't just a quanda, it's a focused training session designed to help you think like a certified Google Cloud ML expert and ace your exam. But first, let's talk about where you're putting your marketing dollars. Stop marketing to the general public. Talk directly to enterprise AI builders. AI Unraveled is the single destination for the senior enterprise leaders, CTOs, VPs of engineering, and MLOps heads who need production-ready solutions like yours. We've reserved a limited number of high-impact ad spots for companies focused on high-stakes, governed AI infrastructure. This is a direct line to your most valuable buyers. Don't wait for your competition to claim the remaining airtime. Secure your package by emailing us today at info@jamgatech.com. Back to AI Unraveled. From life-saving response times to profound questions of privacy and law, we're digging into the technology and the debate. Stay with us.
Welcome back to the deep dive. You've given us some really meaty material today. It looks like a fantastic roadmap for making key decisions in Cloud ML.
That's right. We're looking at concepts straight from the Google Cloud Professional ML Engineer exam syllabus, but the aim here isn't just exam cramming.
No, definitely not.
We're pulling out those core reusable patterns, the why behind choosing, say, Dataflow over BigQuery for a certain task. These are things MLOps pros use day in, day out, really on any cloud platform.
Exactly. So what we're going to give you are 10, let's call them study hacks or rules of thumb, things that map directly to designing robust ML systems. We'll cover the whole life cycle, right? From framing the problem all the way to keeping models running smoothly in production.
Yep, covering the whole spectrum.
Okay, let's dive right in, starting with the absolute basics, the foundation. So first up, problem framing. Imagine a client, maybe in finance, needs a model. They want to predict the exact credit score for loan applicants, a number between 300 and 850.
Right.
How do we even start classifying that type of problem?
Well, because you're predicting a specific number on a continuous scale, the score itself, it's clearly a regression problem.
Okay.
You're asking how much, not what kind. So on Vertex AI, your first thought might be maybe linear regression to start simple, or perhaps jump straight to something like XGBoost for potentially better performance.
Okay, so that gives us our first real pattern, right? Let's call it the what versus how much rule.
Yeah, I like that.
If the output you need is a category like, is this transaction fraud or not? Is the loan approved or denied? That's classification. But if you need an amount, a quantity, a specific score, how much revenue, what temperature, that specific credit score number, that's always regression.
Exactly. Nailing that distinction up front just defines your whole initial approach. It seems basic, but it's surprising how often people get tripped up on that initial framing.
I believe it. Okay, moving on to the data itself. We've got a pretty common but challenging scenario. Transforming a huge data set, say 5 terabytes, of totally unstructured log files. They're just sitting in cloud storage.
Raw data.
And we need to turn them into something structured, usable, needs to be serverless, needs to scale. What's the go-to for that kind of heavy lifting ETL?
For that combination, massive scale, unstructured source, complex transformations, serverless, the immediate answer in the Google Cloud world is Dataflow.
Okay.
It's Google's managed service, built on Apache Beam. It's just, designed precisely for these big, messy data pipelines, whether they're batch or streaming.
Now, that brings up an interesting point. Why Dataflow specifically and not maybe, say, Dataproc serverless? People might already know Spark, right?
That's a great question, and it highlights another key pattern. Let's call it the flow versus query hack.
Flow versus query. Okay.
If your data needs to flow, meaning it starts raw, unstructured, and needs significant transformation, cleansing, feature extraction, maybe joining different sources, Dataflow is your managed serverless workhorse. It handles that complex journey.
Right.
But if your data is already pretty structured, maybe sitting nicely in tables, and you mainly need to run SQL-style transformations or aggregations at high speed, that's where BigQuery shines.
Okay. So Dataflow for the complex journey from raw, BigQuery for faster analysis on already structured data.
You got it. Flow versus query.
Perfect. Let's wrap up this data section with feature engineering, specifically for neural networks. We have a categorical feature, let's say city. The tricky part, it has like over 10,000 unique city names. High cardinality.
Yeah, very high.
How do we prep that for a neural net? One-hot encoding seems problematic.
Oh, absolutely. You just can't use one-hot encoding there. Imagine a vector with 10,000 columns, mostly zeros. It's incredibly sparse, super inefficient for training, makes the model huge. It's just not practical.
So what's the standard solution?
The standard is to use an embedding layer. In TensorFlow or Keras, that's typically tf.keras.layers.embedding.
Okay, embeddings. And that leads to our pattern, the embed high, one hot, low rule. Use embeddings for high cardinality, one hot maybe for low cardinality features.
Exactly. And the reason embeddings work so well isn't just about saving space, though that's a big plus.
What else is there?
It's about capturing semantic meaning. The embedding layer learns to map each city to a much smaller, dense vector, maybe just 16 or 32 dimensions instead of 10,000.
Right.
And during training, the model actually learns meaningful relationships. It figures out that San Jose and San Francisco should probably have vector representations that are closer together than, say, San Jose and Tokyo.
Yeah.
It learns geographical or maybe even demographic similarity from the data.
So it adds intelligence, not just compression.
Precisely. It understands the feature better. #tag2, training and tuning decisions.
All right, data's prepped, features are looking good. Let's move into training. We're using TensorFlow on Vertex AI, but here's the snag. Our code relies on some specific, maybe slightly obscure custom library. It's not in Google's standard pre-built containers.
Okay, a common scenario.
What's the architectural move here?
As soon as you hit a requirement that the standard containers don't meet, you have to build a custom container.
Right, Dockerize it.
Exactly. You package your application code, all its dependencies, including that special library, into a Docker image. Then you push that image up to Artifact Registry, Google's container registry service.
And then tell Vertex AI to use that specific image.
Yep. You provide the image URI when you configure your Vertex AI training job.
That makes sense. So the pattern here is something like the pre-built for speed, custom for need hack.
I like it. That sums it up perfectly.
You always want to use the pre-built containers if you can, right? They're maintained, optimized, simpler.
Faster deployment, less management overhead, absolutely. Always start there.
But the moment you have that special need, a specific library version, maybe custom binaries, a unique OS setup, then the extra work of building and managing a custom container becomes unavoidable. It's a necessity.
Necessity dictates the custom path. Clean decision.
Okay, let's talk efficiency. Hyperparameter tuning. We're using Vertex AI Vizier, which is great, but legit constraints. We can only afford maybe 50 trials in total. We need to make every trial count.
Limited resources. Okay.
Right. What optimization algorithm should we absolutely be using in Vizier?
With a tight trial budget like that, you want the default, which is Bayesian optimization.
Why Bayesian? Why not, say, random search? Isn't that sometimes effective?
Random search can be okay if you have a huge budget, lots of trials, but it's fundamentally, well, random. Each trial is independent, doesn't learn from previous ones. Grid search is even worse on a budget, often wasting trials on poor areas of the space.
So Bayesian is smarter.
Much smarter, especially with limited trials. It builds a probabilistic model of how the hyperparameters relate to the outcome metric. After each trial, it updates its model and uses that knowledge to choose the next set of hyperparameters that look most promising.
So it uses the results from trial 1 to inform trial 2 and so on.
Exactly. Think of it like searching for oil. Random search just drills holes everywhere. Bayesian search drills a hole, sees if it finds anything, and then uses geology principles to decide where the next most likely spot is based on the previous results. It focuses the search intelligently.
Got it. So the rule is simple. Be Bayesian on a budget.
Perfect rule. Maximize what you learned from each trial when resources are scarce. #tag3. Deployment, orchestration, and maintenance.
Okay, models trained, tuned. Now for deployment. We need to get this model onto a Vertex AI endpoint. Requirement. It's got to be super fast, lowest possible latency. Predictions are coming in one at a time, maybe for real-time customer interaction.
Right. The keywords there are real-time, lowest latency, one by one.
So the choices.
That immediately points to online prediction, served via a Vertex AI endpoint. That's the architecture designed for immediate low-latency responses to individual requests.
But online prediction, that means keeping infrastructure running all the time, right? Managing traffic scaling, availability. It sounds more complex, maybe more expensive than other options.
It absolutely is. And that complexity, that cost, is the trade-off. It leads directly to our next hack, the online for now, batch for later hack.
Okay, explain that.
Online prediction is for when now matters. Seconds count. The request needs an immediate answer. But if your scenario involves processing, say, a large file of data overnight, or scoring an entire customer database weekly, or generating a scheduled report, latency isn't the main concern there. Throughput is.
And for that?
For that, you use batch prediction. It's usually simpler to set up, often cheaper because you're not paying for idle resources 24/7, and it's designed to efficiently process large volumes of data when immediate responses aren't needed.
So the dividing line is really that time sensitivity and the associated cost complexity. Immediate need, online. Scheduled or large volume, batch.
Precisely. Clear choice based on requirements.
So let's scale up our thinking. We don't just have one model anymore. We need a full MLOps system, a reproducible, automated end-to-end workflow.
Right.
Think data validation, retraining, model evaluation, maybe conditional deployment based on performance.
Okay. Orchestration.
Yes. What's the go-to service for orchestrating that whole ML lifecycle on GCP?
Whenever you hear words like workflow, orchestration, automation, reproducibility in an ML context on Google Cloud, the answer is Vertex AI pipelines.
Built on Kubeflow pipelines and TFX.
Under the hood, yes. But Vertex AI pipelines is the managed service experience. It's the backbone for defining, executing, and monitoring these multi-step ML processes in a standardized way.
So the pipeline for process rule. If you need a defined, repeatable sequence of steps for your ML tasks, you need pipelines.
Couldn't say it better myself. It's all about automating that process for consistency and reliability.
And speaking of reliability, let's talk monitoring. Our model's in production, but suddenly performance tanks. We suspect the data it's seeing now for predictions is somehow different from the data we trained it on initially.
A classic MLOps challenge.
What's the technical term for that specific failure mode?
That phenomenon is called training-serving skew. It signifies a systematic difference between the statistical properties of your training data set and the data hitting your prediction endpoint in real time.
Like training an e-commerce model mostly on holiday season data, then running it in January.
That's a perfect example. The user behavior, the product mix, everything could be different. The context is shifted. That's skew.
You mentioned a skew drift shift triangle earlier when we were prepping. Can you break those down? People often mix them up.
Yeah, absolutely. They're related but distinct. Skew, as we said, is that mismatch between the training world and the serving world, often noticeable right after deployment. Maybe a feature pipeline bug or just different data sources.
Okay, static difference. What's drift?
Drift, or more specifically data drift, is when the statistical properties of the serving data itself change over time, gradually. Customer demographics might slowly evolve, new types of the products get introduced, user behavior patterns change seasonally, the world changes, and the input data reflects that.
So skew is a snapshot difference. Drift is a gradual change over time. What's the third one? Shift.
Shift, often called concept drift, is usually the most problematic. This is when the fundamental relationship between the input features and what you're trying to predict actually changes. The underlying concept the model learned is no longer true.
Can you give an example?
Sure. Imagine a fraud detection model where, historically, transactions from a certain country were high risk. But then, maybe due to new security measures in that country, transactions from there actually become low risk. The meaning of the country feature related to fraud risk has fundamentally shifted. The model's core assumptions are now wrong.
Wow, okay. Skew. Train versus serve difference. Drift. Serving data changes over time. Shift. Feature-target relationship changes. Critical distinctions for monitoring.
Absolutely crucial for maintaining model health. #VLE, responsible AI and serverless architecture.
Sticking with model health, let's pivot slightly to responsible AI. We've got a classification model maybe deciding on loan approvals, and we need to check for bias. Does it perform differently for different groups, like based on zip code or age groups? We need to dig in, maybe do some what-if scenarios interactively.
Right. Investigating fairness and potential bias.
What tool is designed for that kind of interactive exploration on Vertex AI?
The main tool for that specific job is the what-if tool. It's integrated directly into the Vertex AI platform.
And what does it let you do?
It's really powerful for this. It lets you slice your evaluation data by different features like age or zip code and see how the model performs on each slice. You can compare performance metrics, look at individual prediction explanations, and even manually tweak feature values for a data point to see how the prediction changes the what-if part.
Okay, so that gives us our next hack, the what if for fairness hack. If the task involves interactive bias checking, slicing data for equity analysis, or just understanding model behavior across subgroups, the what if tool is essential.
Non-negotiable for responsible AI practices, really. It lets a human directly question and probe the model's behavior in ways that just looking at aggregate metrics can't achieve.
Makes sense. Okay, final scenario. Let's tie a few things together with a quick architecture design. We need an end-to-end serverless system. The goal: analyze customer feedback messages arriving in real time via PubSub, run sentiment analysis on them, and then store the results in BigQuery.
Okay, classic serverless pattern. Real-time ingestion, processing, storage.
What's the simplest, most common serverless architecture for this on GCP?
The most straightforward way is usually PubSub receives the messages. Each message triggers a cloud function.
The lightweight compute piece.
Exactly. The cloud function takes the message payload, maybe does minimal formatting, and then calls an external API, in this case, probably the Cloud Natural Language API for the sentiment analysis.
Got it. API does the ML work.
Yep. The function gets the sentiment score back from the API, perhaps adds some metadata like a timestamp, and then writes that structured result directly into BigQuery.
And the beauty is, zero servers to manage across that entire flow, right? PubSub, functions, NL, API, BigQuery, all managed, all serverless.
Totally serverless. Scales automatically, pay for what you use. It beautifully illustrates our final pattern, the serverless trigger act store pattern.
Explain that trigger act store.
The trigger is the event coming from PubSub. A new message arrives. The act is performed by the cloud function, which orchestrates the call to the external service, the natural language API, and stores BigQuery, the serverless data warehouse holding the results.
So event trigger, compute action, persistent storage.
Exactly. That pattern, some kind of event source triggering a lightweight compute function that calls another service or model and stores the result. It's incredibly common and powerful for real-time cloud ML applications.
That was fantastic. 10 really critical architectural decision points distilled down into these repeatable rules or patterns. I think the big takeaway is that professional ML engineering on the cloud isn't just about Python code and algorithms.
Not at all.
It's fundamentally about choosing the right managed service for the specific job, considering scale, latency, cost, complexity, and then composing those services using established architectural patterns.
You've nailed it. It's about system design using the building blocks the cloud provides. And maybe before we wrap up, I can leave you with one final thought, tying back to our monitoring discussion.
Please do.
We talked a lot about skew, drift, and especially concept drift affecting ML models, how the meaning changes over time.
Right.
I'd encourage you, the listener, to take that same critical lens and apply it beyond ML. Think about traditional business intelligence. Think about your standard dashboards and reports. How might concept drift apply there?
How could a BI metric drift in meaning?
Well, think about a metric like, say, average user engagement time. Maybe it stays numerically stable for months. But what if, behind the scenes, how users are engaging has totally changed? Maybe they used to spend time reading articles, now they spend the same time passively watching auto-playing videos.
So the number looks the same, but the meaning of engagement has completely shifted. What it represents is different.
Exactly. When does the definition of that metric, the underlying concept, fundamentally break down, even if the number hasn't changed much?
Yeah.
Apply that MLOps thinking about drift and shift everywhere you look at data over time.
That's a really provocative point. Reporting the same number, but it's telling a different, maybe misleading story. A great challenge for everyone listening.
Food for thought.
Definitely. Well, thank you for walking us through these patterns, and thank you, our listeners, for diving deep with us. We hope you can start applying these architectural hacks in your own projects right away.
That's it for today's deep dive. We hope you walked away with actionable insights for your enterprise strategy. Before you go, let me remind you of the unparalleled value of this platform. AI Unraveled delivers deep, uncompromised technical insight that keeps our audience, senior enterprise leaders, tuned in to the very last minute. That sustained attention is the best place for your ad. This is your opportunity for a direct line to your most valuable buyers, the CTOs, VPs of engineering, and MLOps heads who sign off on high-stakes infrastructure. Stop wasting budget on general marketing noise. Secure your high-impact premium ad campaign right here. Email us today to reserve your mid-roll package, info@djamgatech.com. Thank you for listening to AI Unraveled. We'll be back tomorrow with more.